All right, so yeah, so where were we? So we were trying to get to this locally finite refinement given an open cover. And that's because once we have that, then we know how to construct a partition of unity. You just put bump functions on every open set in that cover, and you construct a function on your manifold by adding them up and sort of normalizing so that when you add up these phi's, then you get one, right? So that's how you construct a partition of unity, but you have to make sure that this summation makes sense, and that's sort of guaranteed by locally finite, right? So locally finite is what I've described here. So each point in the manifold will belong to only finitely many of these open sets, right? And and um, and the way that I we started was to sort of start with some the fact that there is a basis um, which is countable, and each of the open sets in the basis has compact closure. So that's sort of possible as sort of part of this um, this warm-up lemma, and which I left as an exercise. And the second thing that I also sort of told you how to do is once you have such a countable basis by comprising open sets, compact closures, you can create an exhaustion, compact exhaustion, where you have these nested sequence of open sets, each of which is sort of the closures of which are contained in the next open set, right? So that's the, so maybe I should, maybe I'll add one more, sort of the GI plus one is here and GI minus one is here, and it's a sequence and covers the whole manifold. All right, and so once you have such a thing, then it's not hard to construct a local cover. What you do is you can do the following. So you kind of yeah, so what's the proof of the lemma now? So you can so you can observe that if you look at GI closure, which is a compact set, minus GI minus 1, so that is a compact set, right? It's an intersection of closed sets, so it's closed, and one of them is compact. So this is a compact set, and it's a subset. It's contained in this larger kind of annular region. GI, this is an open set. This is an open set. So the way that maybe let me draw that part again. So sort of so you have, let's say this is GI minus 2 here, so GI minus 1, GI plus 1, etc. So somehow the region we are looking at, the compact set that I'm talking about is sort of this kind of region. Okay, so it's sort of, and this is contained in this sort of bigger open set, sort of bounded by this. And so the bigger open set, which I've defined like this, okay, GI plus 1 minus GI minus 2 closure, okay? And so this is true. Maybe I should sort of careful about the indices here. So this is, so maybe sort of here, sort of I is bigger than equal to 3, so that everything makes sense. After all, we started our exhaustion by G1, all right? Okay, so and then what you do is so for each, so you consider the open, you take this open cover that you already given, and you look at the intersections of these with these open sets. So with this open set here, okay. So let me just say, so we fix an I. So maybe for each I bigger than equal to 3, consider this collection. So this is an open cover of um, of this compact set. All right, because this, so the open sets U alpha, they cover the whole manifold, but now we are intersecting with this particular open set. So it'll certainly cover this open set here, which contains our compact set. Okay, and now you have an open cover of a compact set, and this, therefore, you know that you'll have a finite subcover. So you get a, this has a finite subcover. Okay, so you get finitely many open sets for each of these i's. Okay, and each of these finitely many open sets will sort of cover this sort of kind of green region that I've marked here. Okay, and then you just take a union of, for each I you have this finitely many sets, and so together, for all of this gives you a countably infinite set, and which covers the whole thing. You might sort of, we missed a little bit out on the where you start off things. Remember that here sort of I is bigger than or equal to 3, so you throw in a little bit more, perhaps. So you have, so I guess sort of there's G1 sitting here, and so the way that we've done it is, so maybe we start at G2 and sort of the region between G2 and G3, but then, remember the G2 closure. So let me just say add a few more sort of finitely many sets to cover sort of the what remains, so which is probably G2 closure, right, which is contained in G3. So you just G2 closures, again, compact, so the same sort of procedure as before. You'll get some finitely many open sets covering G2 closure, and you throw that in, and so those together with those union of all these finite sets that I described will form an open cover, and this is the open cover we are after. So first of all, this is a refinement, because sort of each of these open sets, it's an intersection with U alpha, so it is certainly contained inside U alpha. So these are smaller open sets, and then it's not hard to see that these are locally finite also. So if you take, so pick any point in your manifold, it'll lie in one of these green regions for some I, and it'll be in one of the finite sets we chose for that I, right? Because well, I guess it could also, I mean, it'll be, so at most it'll overlap with some other open sets for the next, oops, sorry about this, yeah. So at most it'll overlap with some open sets for this next I and the previous I, okay? But it won't intersect with anything, beyond that, because of the way we construct things, okay? So this is, so each of these, in this sequence of finite sets of finite collections of open sets that we've constructed. So each of these, for each I, so these guys, they won't intersect too many others, right? So this collection will intersect perhaps the connection for I plus 1 and I minus 1, but not beyond that. Okay, and so this makes sure that this is locally finite. All right. And so this is how you get a locally finite refinement, and once you have that, as I said, you can construct your partition of unity. All right. So this is sort of, the whole thing is sort of an exercise in point set topology, and it's fairly straightforward. And the key thing is second countability. All right. Okay, so I leave the sort of the rest of the. I mean, if you want to really write down what the partition of unity is, so that you can use this idea and, as I said, use bump functions and add them up. And so this is something that I'll leave as an exercise. All right. Any questions? Okay, so if not, let's look at some. I mean, these partitions of unity are quite useful. One of the things that we can talk about as an application is the fact that every smooth manifold admits a smooth exhaustion function. What's this exhaustion function? Well, it's a smooth function. So that's why I've said smooth here. So the smooth function, so real valued function, so that if you look at sub-level sets, let's call the sub-level sets M subscript C, it's all the set of points so that function value is less than equal to C. Did anyone have a question? Okay. So this is compact for each C in R. All right, so it's like you can kind of imagine the manifold to be maybe non-compact. It's going off to infinity, and sort of you can define some function, something like a height function. Yes.
Can you please reshare your screen? I was kicked out of the meeting somehow, and I cannot see it anymore.
Okay. Let me try to reshare it then. Can you see the screen now?
Yes, sir. Thank you.
Okay. All right. So yeah. So what's going on is maybe something like this, where you pick a pick a value C. So all the points where the function value is less than equal to C forms a compact region, and so on. Okay. So this, as C increases, these pre-image sets, these sub-level sets, so this is, let me just say, this is something like F inverse of, minus infinity to C. You can think of it that way, right? So these regions are, so I want to set it up so that it's compact. And actually, we can, so in the way that we'll construct it, it's going to be a positive function anyway. So it's something, maybe I should just write it as a positive, or sorry, a non-negative function, so that maybe the discussion is slightly easier. So so this is sort of all non-negative functions. So it's a pre-image of these compact sets, right? Of compact intervals. Okay, and then these are required to be compact. So this is something like a height function, if you like. All right, and so the way that you can now sort of construct such a thing is again, you start with some, I'll call it Vj, but maybe I should have called it Uj. It doesn't matter. So it's a J belonging to N. This is a countable open cover by pre-compact open sets, right? So open sets whose closures are compact. So this is something that we know now that, they exist. So in fact, you can do better, right? You can always find a refinement of a given open cover but here there's no refinement involved. It's just, you just pick some countable open cover, like pre-compact open. So maybe you pick the basis that you know exists, and then you can find a partition of unity subordinate to this cover. So let me call it J be a partition of unity subordinate to this cover, and you can define the smooth function by adding together these functions with coefficient j sitting in front. So although I've written it like an infinite sum, this is actually a finite sum for any x, because these phi j's. Okay, maybe I should also have said locally finite somewhere here. So countable open cover, which is locally finite. So each point x will belong to only finitely many so let me just write. So by pre-compact open sets, which is locally finite.
Yeah.
Right?
Sure.
Yes.
Yeah. So haven't we already proved that like any open cover has a refinement like which is locally finite like?
Yeah. Yes.
Yeah. So like so the like we don't exactly need to mention this, right? Like this will automatically be.
Yeah, that's why I said let this be a countable open set, right? So we already know such a thing exists. All right. So so yeah, so you have a so the key thing is that you can define your function this way, and this works. Okay, so this is your smooth exhaustion function, and just to so the thing to note is that this for any x, this is actually a finite sum as before, and the point is, since we've thrown in this j in front of it, this makes the the function get bigger and bigger as you sort of take more and more of these open sets. Okay, so in other words, let me just sort of say why this has the property that we want. Well, if you have so suppose you pick some x which is outside the union of n of these, capital N of these Vj closures. All right. So then we know that phi j of x will be 0 for any j in this range from 1 to n, right? Because it's not in the support. So the support. So this is again something maybe I should recall here. Sort of recall that. What does subordinate to this cover mean? Well, it's sort of phi j. The support of phi j is contained in Vj, right? So if something x, little x is sitting outside all of these Vj's from 1 to n, it's not going to be in the support. So Vj is going to be 0 for all of these. So then if you think about what this f of x would be, well, it's going to be so if you try to, so the first n terms vanish. So so it's going to be something like this, right? And sort of j, x, and so each of these j's are bigger than n, and what you're left with is something from I mean, you can think of 1 to infinity phi jx, but the first n terms are anyway 0, so it doesn't really matter. But if I write it like this, then remember that this equals 1. It's a partition of unity. So this shows that whenever you're outside the union of these n compact sets, then you're automatically bigger than n, right? This is exactly the sort of thing that you want. So the kind of the contrapositive would mean that if you're less than n, right, you have to belong to one of these, to this compact set, which is the union of these n of these. Okay, so in any case, I mean, this sort of, if you define your function like this, it's not hard to see that this function is going to get bigger and bigger, sort of as you sort of have more and more of these phi j's in the picture. But each point in the manifold belongs to only finitely many of these phi j's. So you're kind of going further and further out in the manifold, and that's exactly what you want for a smooth compact. So sorry, a smooth exhaustion. Okay, you want those pre-images, these sub-level sets to be compact, right? And so this is a useful fact. It's going to be used, without proof later on, I'm sure. So we're going to sort of assume there exists. Whenever you have a manifold which is non-compact, you can always sort of construct a smooth exhaustion function, and then it's useful because you can treat it. So each of these sub-level sets are compact, and so compact sets, as we'll see, are nice, and so you can, even though the manifold itself was non-compact, you can sort of use things about compact sets and to deal with them. Okay, so you can make these compact sets bigger and bigger, so till they exhaust the manifold. This is what the smooth exhaustion function is useful for. Okay, so that's one application, and there are others. So in general, so I wanted to do this, but maybe I'll skip this for now. So I wanted to, so maybe I'll mention this, but the point is the partition of unity can be used to glue together some maps defined on charts to obtain a global map. All right, and so this is the sort of thing that we just saw actually in this construction, and the kind of the general thing is that if you have, let's say you have, so let me just say a little bit more here, so that so suppose you have a partition of unity, which is, I don't know why these notifications. Okay, so if phi I belongs to n is a partition of unity subordinate to some open cover of M, and suppose you start off with a collection of functions defined only on these open sets. Maybe they're not functions, maybe they're maps. The maps going to Rn, or smooth maps for each I and n. So then we can define a global map by saying that g of x is the sum of phi I of x times gi of x from I equal to 1 to infinity. And once again, this is going to be actually for every x, this is just a finite sum, because these phi i's are supported on some locally finite refinement of these ui's. And so this makes this right-hand side actually is a finite sum. It makes sense for every x, and it's easy to see that it's actually a smooth function also if each gi is smooth. Phi i's are by construction smooth, and so this finite sort of products and sums of smooth functions is smooth, and this is now globally defined. Okay, so this is something from from M to Rn. All right, so this is some useful thing that will, sort of happen quite often. And one of the things one can prove with this is this approximation theorem. Well, maybe, we'll skip it for now, but so we can, let me just say we can prove this. An approximation theorem is something like so if you start with a continuous map, a continuous function, then you can approximate it by, so can be approximated by a smooth function. This is often useful because, when you're dealing with smooth manifolds, you want things to be smooth. If you, sort of happen to have something which is just continuous, well, you can replace it with a smooth function which is close to f. And what does that mean? So let me just mention what smooth function is. So let's call it G. And so here you can define approximation in different ways. But one of the easiest is sort of approximation in the C0 norm or the sup norm. So this is less than epsilon for all x and m. Okay, so this is G is smooth, and it's close to your original f. Okay, and then you can do this by it's easy to approximate a continuous function by smooth function in a little piece, and like an open set, if you collection of charts covering your manifold, you can sort of easily approximate on each of these the charts, and so you get a collection of functions like this. You can actually choose constant functions to approximate it locally, and then you can sort of use a partition of unity to add them up like this and get a globally defined smooth function. And that's going to, if you've chosen your local functions to be good approximations in that on those open sets, you'll find that you've gotten something which is globally it's close to your original function. So this is sort of another thing that you can do using partition of unity. And maybe sort of leave you to fill out the details, and perhaps if some point we run into things about approximations, etc. So we'll sort of discuss this part again. All right. So are there any questions about partition of unity and things like that? Otherwise, let's move on. Let me update the lecture notes on the website. Yeah, so I see a hand up.
Hello, sir.
Hello.
Yes, sir. I was asking that when we define the global function from the bump functions,
yeah,
in the partition unity, so we need to ensure that the denominator is non-zero, right?
Yeah, that's you mean where's the denominator?
So like we define the global function as phi I by summation of phi I.
Well, so here there is no denominator. The way
Not here, in the construction of partition of unity.
Okay, the construction. Yeah, absolutely, of course. Yeah, so certainly, yes. So, but so the way that the bump function works is, is that it's yeah, that's right. So yeah, you have to be careful, right? So you have to choose. Yeah, you have to choose your open sets. You're quite right. I mean, you have to be careful, and you have to make sure that your denominator. So in other words, you have to make sure that every point in your manifold, right, belongs to some part. Belongs to some open set, and not only that, it belongs to part of that open set where the bump function is positive, right? So that's important. Yeah, you're absolutely right. Okay, so but that can be ensured. You just need to sort of choose, sort of a suitable You just need to define things suitably. Just sort of have a covering with slightly smaller open balls where you know that the bump function, remember that the bump function is going to be definitely positive in a slightly smaller open set, right? It's going to be, sort of something. So it's zero
Yeah, and we
outside,
have
it's
also,
one there. Right. Yeah.
yes, and I was also saying that we have also defined the bump function only for balls, right?
Oh, well, the way we defined it for cubes,
I
right?
mean for cubes, yeah. And in the construction of the locally finite subcover, we have to ensure that it's covering by cubes, right?
Yeah, but these cubes are contained inside balls, so it's fine, right? So you kind of, yeah, so that's okay.
Okay.
So you can go back and forth between cubes and balls if you want. Yeah, but you're right. So you have to make sure that you're covering by some open sets in which their bump function is positive. So every point in the manifold must belong to some such slightly smaller perhaps open set. So anyway, so that can be, it's not hard to sort of arrange that. So this is sort of part of what this this exercise is about. Okay, so it's not it's not it's not complete. That's the idea of the proof. Summation of phi i's divided by, sorry, phi I divided by summation phi i's. But to make it work, you'll need to do a little bit more. Okay, yeah, that's a good question. Anyone else? All right. Okay. Yeah, so I mean, so some of these things I'm leaving to you because I expect people to work out the details. But if you have trouble, let me know. I'll kind of adjust accordingly. All right. So today I wanted to, sort of half the class is already over, but I wanted to review some multivariable calculus. Right? So sort of this is things which you would already know, but I thought that I'll do that just so that everybody is on the same page. Okay, so let me recall some very basic definitions. So what do you mean? So multivariable calculus from Rn to Rm. The whole point of part of this course, as I mentioned, was to make sure that we can develop the machinery to do all that we do in Rn. So we can now do in manifolds, right? So we kind of, that's what this calculus on manifolds is about, and which is sort of part of what we'll see. Okay, so just let me quickly recall. So first of all, something is differentiable at a point A. Of course, you can also, sort of define. So here I've taken the domain to be the whole of Rn, but you can take to be some open set U contained inside Rn if you want. You can define differentiable there, but the definition is that it's differentiable if there exists. Oops, let me choose some other color. If there exists a linear map, we call it linear transformation. DAF, that's like the derivative at the point A. This is a linear map from Rn to Rm. Now we're thinking of Rn and Rm as vector spaces. So you can think of linear maps. And this linear map approximates capital F to first order. And sort of that's kind of one way to think of this, sort of the usual notion of derivative that you learn. You can think of it as saying that, if you look at this difference of fa plus h and fa, then that's, okay, so I switch to small f here, so maybe I should capital F. So that's this divided by mod h is 0. right? So that's what, I mean, so approximately, so so FA plus H is, looks like FA plus H plus some sort of lower order terms. Right. So here, this maybe I should write a double bar here. So this is sort of the norm in Euclidean space, right? So that's the norm. All right. So that's differentiable. So I'm sure everyone knows that. And also let me remind you of partial derivatives. So you can talk of partial derivatives in the different coordinate directions. So the jth partial derivative of f at a point A, I can think of this, I can write as a gj. Let me actually shift to little f. This little f is our smooth map between Rn and Rm. And you can talk of this, well, by definition, is you're just sort of moving in the jth factor, jth coordinate rather. Okay, and taking the difference, and this is the usual derivative, keeping all the other coordinates constant divided by h, if it exists, right? So this, right, that's the partial derivative, and the point is that if something is differentiable at a point A in this first sense, then all these partial derivatives do exist at A. Let me just write at A. And in fact, you can, these form the columns of that linear transformation if you write it as a matrix. Okay, so let me just say, and sort of d a of f, that matrix would look like dj fi. This is going to be a m cross n matrix, or rather n cross m, right? So and it's the partial derivatives will be all the sort of these entries. Okay, so so that's what happens when something is differentiable, and it's also, let me maybe add in here, so it's smooth. So remark is that sort of the f is smooth if all these partial derivatives, the entries of this total derivative, this matrix, are smooth functions. Okay, so you can think of a smooth map from Rn to Rm as being not only that it's differentiable, but this derivative matrix that you get, whose entries are all these partial derivatives. So each of these guys, these dj of fi's, these are all smooth functions. Okay, so infinitely many times differentiable functions from R to R. Right. So all of these, these partial derivatives. I should mention that these are, the things where you, if you give it a number, you get out a number, right? So these are functions from R to R. All right, so so here's just to make sure that this notation doesn't confuse people. So here's an example, very simple example. So suppose I have this function this is from R2 to R2. Then the partial derivatives, are something like this. And the so here it's sort of true at every point. I should say that so all these are that I mentioned were differentiable at a point. Here exists at A, etc. But if it could be so differentiable at A. But if I just say differentiable, it just means everywhere in the domain where it's defined, something like that. So here this is actually sort of some, well defined everywhere in R2. I can sort of, I'll avoid writing A here, it's not necessary. But so at any point the matrix, let me say at x comma y, this linear transformation that approximates f, this derivative of f, it looks like the matrix where it's 2x, y, these partial derivatives with respect to the variables define the columns of this total derivative matrix. All right, and this is minus 2y x. All right, so this is, and anyways, this is something that you must have all seen. Yeah, so I already mentioned what smooth is, so maybe I'll skip this now. All right, and here are some basic facts. The first basic fact is that if you have a constant map from Rn to Rm, then the derivative is 0. This is easy. Then you also have that if you start with a map which is a linear transformation to begin with, then of course the derivative approximates itself the best. So some other approximation is itself. So the derivative is f. All right. So this is another fact. Then you have the chain rule. This is always good to keep in mind. We'll probably use a lot of this during this course. So this is when you have two maps, two smooth maps, and you have a composition. Remember that the composition G composed with F. So this is also going to be smooth, and the derivative of this composition at any point A is, maybe I'll write A as over here. Okay, so this is a matrix at every point A. So this is can be thought of as the composition of two derivatives of these intermediate maps. So as follows. Okay, so you look at, so this is A going to G compose with f of A. So it sort of breaks up into two steps. So you first look at this map F, and you can talk of the derivative of that map, that's df of A. And then you're looking at this map G at f of A, and looking at that derivative. And then you get two linear transformations from Rn to Rm and Rm to Rp, and you can compose them, and that's going to give you the final the derivative. Okay, this is something you've all seen in single variable calculus also. In single variable calculus, you have something like G composed with f prime of x is G prime of f of x times f prime of x. Okay, so this is what it boils down to. All right, and so maybe one more fact I should sort of add just for completeness before I go on to the inverse function theorem is, so if you, these derivatives sort of have this kind of behave nicely under addition and multiplication of functions. So if you have two maps, both are, let's say, differentiable at a point A, then if you add them up, the derivatives of the addition of the two functions, just the addition of the derivatives. This is G of A, and if you take a product of the two functions, so maybe here I should maybe I'll yeah, so maybe I should have kept one of these to be anyway, so there's also a product rule. And well, here, let's say, I mean, so let's say the product rule, talking of sort of the case where you have functions, and Rn to R, then the product rule. Then multiplying functions makes sense, right? You're just multiplying by a real number, and then the derivatives just get, so each of these is real numbers. This is going to be a vector, and these get added up. All right. So anyway, so the sort of these, you can figure out what happens to derivatives if you do various operations on your functions. All right, and maybe before the inverse function theorem, one more fact I should mention is the mean value theorem, which is well, if you have this kind of so suppose you have a function defined in an open set in Rn, and so this is sort of f, let's say f is a differentiable function. Then wait, let me push this below. Then if you if you take, suppose you have a point A over here, and you have some kind of interval A plus H. H is some other sort of vector in Rn, if you like. So this interval contained inside U. So then if you look at the difference of the function values of the two endpoints of this interval, it's going to be related to, so if A plus H are endpoints of a line segment in U, where so for some C in that line segment, so there's going to be some C, so that the difference of these function values is precisely this, okay? And this is easy to prove. I mean, if you assume the same statement in single variable calculus, which you all know, you can just use that, because the function, if you restrict if you restrict this function to this line segment, it's now boils down to a single variable function. And then if you apply the mean value theorem here, you get what you want. Okay, so I won't go into the proof of the mean value theorem, which I'm sure you know, but let me just mention that one corollary is that, so if you have something defined, so if you have a bound on the derivatives, all these partial derivatives of f on some domain where things are defined, so for convenience, I can define, so let's assume that, sort of your function is defined on a rectangle instead of this open set, which I've chosen, some kind of open rectangle, perhaps. It's, okay, so that's definitely going to have the property that, sort of, if you take 2 points inside the domain, then the line segment between them is contained in it. So if you have this bound on all these derivatives, then the difference in two function values is always going to be less than, so this some C times x minus y. Maybe I should just say m times, but maybe it's twice of m, so I'll just say C, okay, for some. Okay, let me just write the quantifiers correctly. So if you have these bounded derivatives, then there exists a C such that this happens for all x, y, and a. Okay, so so this is sort of immediate because what happens is sort of this side, this all the entries of this is going to be some kind of a column vector, row vector, depending on how you kind of set it up. Now this is going to be all the entries are going to be bounded, all right, and so when you this so when you multiply out, this is going to so the C will depends some constant that depends on m, and once you have a bound on all the derivatives, so this difference this side is bounded in terms of how far you go. All right, so this is useful to know. So very often we'll be sort of, and so this bound very often holds because if you restrict yourself to, for example, a compact set, right? So suppose your rectangle is contained inside some compact set, or the rectangle has a compact closure, something like that. So then automatically a smooth function would have some bound, right? And so you can think of, so all of these, this f would automatically satisfy some kind of Lipschitz property like this. Okay. All right. So now, so the most important theorem that we need to review is the inverse function theorem. So so let me remind you that what this says is that so roughly speaking, so it says that if the derivative, this linear map at a point is invertible, then the map is locally invertible. Okay, so you can define locally. There'll be it's going to be injective and it's going to have a smooth inverse. So that's the inverse function theorem. So let me just mention more precisely. So suppose you have, now let me define things on an open set, define the function on an open set. So here's your function, capital F. And yeah, so so right now, sort of the domain and range have the same dimension, n. Okay, so this be a smooth function. And let's say assume that, at a point P has the property that the derivative at P, I guess I kind of already I'm using two notations for that, but I hope that's not a confusion. So this is sort of the same. So this is a derivative, that's a map from Rn to Rn here. So suppose this has the property that this is invertible. Okay, so then the inverse function theorem says that there exists neighborhoods V of P and W of F of P such that so the restriction of F to these smaller neighborhood V goes to W, and this is actually a diffeomorphism. So in other words, that is sort of F restricted to V is injective, so it's invertible in that sense as a set at least, and this inverse map is actually differentiable also. Okay, and of course it follows from the chain rule that what's the derivative of this inverse map? The inverse map derivative is the inverse of the derivative, right? So this is at f of p. This is p, and this follows from the chain rule because you know that the composition of f and f inverse is the identity map. So this part that I just mentioned is a consequence of the chain rule that I just mentioned. Okay. Now, yeah, so I guess I wanted to give an idea of the proof of this. I'm sure all of you have seen the proof, but now we're running out of time, so maybe I'll leave that to the next time. But let me just mention a couple of remarks, perhaps. The fact that so it's not always, it's not necessary that the derivative is invertible for the function to be invertible. So in other words, f inverse may exist even if the derivative is not invertible as a set. I mean, as a continuous map, it might exist. So it's not going to be differentiable necessarily. Yeah, it's never going to be differentiable if f is differentiable. So let's sort of say what I'm talking about. So if you have f, this is some function we've already seen as a f x going to x cubed. So then this is a smooth map, of course, and a derivative at point 0 is not invertible, it's 0. But there is a continuous inverse to this. This is a homeomorphism after all, because you can define it to be the cube root of x. But this is not differentiable. The point is that it's not differentiable. It can't be, because if it was differentiable, then it would mean that that because the chain rule must hold, it would have forced the derivative to be invertible, but the derivative is not invertible. It's 0. Okay, so in any case, this is something to keep in mind. The final thing keep in mind is that we can only conclude something is locally invertible, even though, let's say, at every point in the domain your derivative is invertible, doesn't mean that globally your function is invertible. It just always means that there exist these open sets, V and W, in the neighborhood of which it's a diffeomorphism. It doesn't mean that there's a diffeomorphism from the whole domain to the whole range. And an example of that is, so suppose I talk of maybe R2 minus, well, okay, so let me not talk about the domain. You can sort of think of the domain, what the domain ought to be. But I want to define a map, sort of R cosine theta, R sine theta. Okay, and the derivative. So this would, you can easily compute the derivative, and so maybe I'll sort of talk about the domain. So maybe the domain is something like 0 to 4 pi, okay, to R2. All right, and this is going to be at every point in this domain. The derivative is going to be invertible, non-singular. But this f, the written here, is not one-to-one. It's not injective. That you can easily figure out, because I'm taking it from 0 to 4 pi. So every time it goes around 2 pi, it go to the same value. So it's only locally invertible in general. Okay, so anyway, so let me stop here. And if any of you have questions, you can ask me now.